Hi everyone! Thank you so much for tuning in today, and thank you to UFA for inviting Georgia Mason, Andrea Polanco, and I to speak at this event. Today, I'm going to be talking about the potential of home cage behaviors and morbidity and mortality data as indicators of cumulative welfare. But first, what is cumulative welfare? As you will have already heard from other speakers, cumulative welfare is the sum of all positive and negative experiences in an animal's lifetime. Positive experiences being those that are preferred or promote fitness, and negative experiences being those that are not preferred or reduce fitness. The goal of cumulative welfare assessment is typically to be able to determine whether an animal's life is worth living, or whether they should be retired or euthanized instead. In rodents, this might be important for senescence studies, animals kept as breeding stock, or in fragile strains. So, what makes a good cumulative welfare indicator? A good welfare indicator shows construct validity. It measures what it claims to be measuring. One way to assess this is to see if the indicator changes in one direction if you expose animals to more positive experiences, again, those being preferred stimuli that boost fitness. This assumes that those stimuli are pleasurable and associated with positive emotions. If the level of the indicator goes down in response to positive experiences, like in the top graph, where we can also see that the indicator continues to drop as the number of positive experiences increases, then we also want it to change in the opposite direction if we expose animals to more negative experiences, again, being those that are aversive or reduce fitness. Ideally, we'd be looking for something like the bottom graph, where the level of the indicator increases as the number of the negative events they experience go up. And finally, we could see if the indicator similarly varies in humans reporting positive or negative emotion. We also ideally want to avoid welfare indicators that are prone to false positives or false negatives. False positives or false alarms are cases where we mistakenly identify a case of poor welfare where suffering is not occurring. This can happen if a negative welfare indicator increases during positive or neutral emotional states. On the graph, that might look something like this. And again, we want to avoid false negatives. These are cases where we're missing situations where negative welfare is occurring. This could happen if a negative welfare indicator decreases, so going in the wrong direction, or doesn't change at all, thus missing a case of poor welfare. On the graph, that might look something like this. So in line with this validation framework, are there any potential indicators so far for cumulative welfare? Well, hippocampal volume, the brain area colored in red on the diagram to the right there, and telomere length, DNA protein complexes at the ends of chromosomes, do show promise as biomarkers of cumulative welfare. This is because they increase or stay stable when animals are exposed to positive experiences, and they can decrease if you expose animals to more negative experiences. And in humans reporting positive or negative emotions, they seem to vary in the same way. But these biomarkers do have limitations. So first, they're invasive, so they can negatively impact animal welfare by requiring restraint and handling. They're also prone to false positives, so shortened telomere lengths are associated with things that are reported as pleasurable in humans, things like smoking or alcohol consumption. And they're also prone to false negatives, so missing cases of poor welfare, and this is because they can be increased or protected by physical activity. So something like hippocampal volume can be increased by abnormal repetitive stereotypic behaviors, which are signs of poor welfare. The same could be true for telomere length. This has already been shown in mink, so animals with high levels of stereotypic behavior, like the two shown in this video here, have elevated levels of hippocampal neurogenesis. If this is true for rodents too, which would make sense, then one potential indicator of cumulative welfare is contradicting or canceling out another, which isn't great. But our working hypothesis is that there are multiple potential cumulative welfare indicators, and their value or effectiveness depends on the strain or species that you're working with. So our focus is to identify more practical indicators that have potential for assessing cumulative welfare. The two that we're most interested in are the use of home cage behaviors and morbidity and mortality data. Starting with home cage behavior, some behaviors reliably occur at higher levels in suboptimal conditions than welfare-friendly ones, and these behaviors are typically thought to be signs of poor welfare, and they're already used in several welfare assessment schemes. Potential indicators of cumulative welfare for rodents might be stereotypic behavior or time spent inactive but awake. We're going to be focusing on stereotypic behavior since it's better studied. Stereotypic behaviors are abnormal repetitive behaviors that appear to have no function. In rodents, they can take several forms, but two common examples might be bar mouthing, which you can see in the mouse on the left here. She's actually mouthing the hopper. Or root tracing, which you can see in the gray mouse on the right, and she's incorporated a backflip into her root. These are widely accepted as indicators of poor welfare, but how do they relate to cumulative welfare? So, sticking with our validation framework, stereotypic behavior does appear to increase in response to aversive events in several species, and it does appear to decrease in response to positive events. In elephants, these abnormal behaviors increase with the number of zoo transfers that an individual experiences. In laboratory primates, stereotypic behaviors can also increase with exposure to aversive events, so being involved in many projects or experiencing many room moves or pair separations can all elevate levels of stereotypic behavior. However, recent attempts from our lab to replicate this have failed. For primates, positive experiences, like more time in outdoor housing, can also reduce the levels of stereotypic behavior. However, again, recent attempts to replicate this in our lab were not successful. In deer mice, environmentally enriched cages like the one on the right typically protect against the development of stereotypic behaviors. So as you can see in the graph below, as animals age, levels of stereotypic behavior go up for standard house mice, the beige line on top, but this does not occur for enriched animals. If enriched animals experience 12 hours of isolation per week throughout their lives, though, in a chamber that looks like this, the protective effects of enrichment vanish, and you can see in the graph on the right that enriched house animals develop similar levels of stereotypic behavior to standard house animals. It's important to note, though, that there was no difference between standard house mice that experienced this isolation and those that didn't, which suggests there might be ceiling effects of stereotypic behavior, as though the levels of stereotypy reach a maximum and then at a certain point additional stressors have no effect. On the other hand, stereotypic behavior can decrease with positive events for deer mice. Again, we know there's a protective effect of preferred environmental enrichment from the last study, the same graph shown below on the left here, and we also know that enrichment reduces stereotypic behavior in animals moved from standard to enriched conditions, which we can see in the center group in the graph below here. In laboratory mice, stereotypic behavior can increase with exposure to aversive events. Again, increased time in standard housing can increase levels of stereotypic behavior. In the graph here, we can see that as more time is spent in barren cages across the x-axis, that the levels of stereotypic behavior go up. However, we suspect that there might be false negatives in strains that aren't prone to stereotypic behavior. In mice, stereotypic behavior can also decrease with positive experiences, so environmental enrichment protects against the development of stereotypic behavior, providing standard house mice with enrichment lowers their levels of stereotypy. And in the graph below, we can see here that mice who are most willing to push heavy weights to access environmental enrichment also show the greatest relative decrease in stereotypic behavior. So the more that mice value enrichment, the more effective it is in reducing their levels of stereotypic behavior, which is pretty neat. So, stereotypic behavior definitely has potential as a cumulative welfare indicator. When we see stereotypic behaviors, we know they're signs of poor welfare. But we also suspect that these behaviors might protect animals from shortening telomeres and hippocampal volume loss, and stereotypic behaviors are prone to false negatives, potentially as a result of ceiling effects, but also because not all animals develop stereotypic behaviors. Because of this, it's important to consider other behavioral responses. So, in suboptimal conditions, some animals like C57BL6 mice, rats, or guinea pigs can develop stereotypic behaviors, but they're often not prone to doing so. These animals might instead show hypoactive responses to stress, characterized by inactivity. This is why time spent inactive but awake, or IBA, could have potential as an alternative indicator of cumulative welfare. Here, you can see that the center mouse is lying still with her eyes open, IBA. We expect that high IBA mice would show hippocampal volume loss and shortened telomere length associated with poor welfare. However, inactivity as an indicator of cumulative welfare hasn't really been investigated yet, so here we are wondering whether other indicators could be considered instead. One option might be the use of colony morbidity and mortality data. High morbidity and mortality rates are often associated with negative emotional states, but, as reviewed by Walker and colleagues, negative mood and emotion themselves can play a causal role. This relationship is likely a result of the fact that chronic stress and associated negative moods can cause long-term up or down regulation of the HPA axis and upregulation of the SAM axis, and this prolonged activation can cause problems. There's plenty of evidence that morbidity and mortality increase in response to aversive events. In humans, stress increases susceptibility to many conditions, including cancer, HIV, and cardiovascular disease, and it also increases mortality rates of those experiencing them. Similar phenomena occur in animals as well. Rhesus macaques with simian-acquired immune deficiency syndrome that experience unstable social groups live shorter lives, and Asian elephants that experience early maternal separation and moves between zoos can increase mortality too. It's important to note here that the ways in which stress kills are very diverse, and mediated by many different diseases and experiences. This highlights the fact that there's no one sign of cumulative stress, and as a result, all-cause mortality might be very useful. Morbidity and mortality rates also decrease with exposure to positive experiences. So in humans, people who self-report being happy live longer, and they have higher levels of education, and they're at lower risk of suicide or disease mortality. And in animals, zoo orangutans that are subjectively rated as happier by their keepers have longer lifespans, and so do bold or confident dogs and exploratory rats. There's also a great deal of evidence that enrichment has positive effects on rodent lifespans. So we already know that enrichment protects against signs of poor welfare like stereotypic behavior, but it also protects rodents from diseases, lowering mortality rates from implanted tumors or stroke. And enriched rodents can also live longer even when they're not used as disease models. So enriched CD1 females have longer lifespans, and both social contact and running wheels can improve rat longevity. In our own lab, we decided to investigate these effects in laboratory mice. In a recent study funded by UFA, we used 165 female mice from 3 strains and reared them to adulthood in either large environmentally enriched cages, shown above, or standard bearing cages like the one shown below. At 570 days, so approximately a year and a half of age, 38% of mice were killed so that their brains could be used to test other hypotheses. 39% were adopted out, but at this point, 23% of mice had died unexpectedly or prematurely. Investigating these deaths revealed a significant housing effect. Just under 65% of non-enriched mice were still alive, compared to just over 80% of environmentally enriched mice. This steep drop at the end here is the date when they are adopted out or perfused, not a mortality event. Furthermore, mice housed in non-enriched conditions were more at risk of premature death, and for these non-enriched animals, stereotypic behavior also predicted early death, with highly stereotypic animals being most at risk. However, stereotypic behavior didn't completely explain this housing effect. We also didn't detect a relationship with IBA, but we hope to be able to assess this in the future with mice that are allowed to live their full lifespan. This will be a long project since some of the enriched mice from our last cohort that were adopted out lived until they were over the age of 3 years old. Overall, morbidity and mortality also have good potential as indicators of cumulative welfare, but these results can only be used for future planning, not for interventions for the animals that generated the data. Further, like other indicators discussed, these are also at risk of false positives and false negatives. False positives are a concern because sometimes mortality rates increase even when welfare is not compromised. So thrill-seeking behavior or being male in humans causes elevated mortality, and in animals there are plenty of species and strain differences in lifespan that reveal nothing about welfare. False negatives are also a concern because mild stressors are not often detectable through morbidity and mortality rates, meaning that cases of poor welfare could be missed. What we really hope you take away from this is that the relationship between potential indicators of cumulative welfare is complex and variable and definitely needs more research, and there's likely no one-size-fits-all rodent cumulative welfare indicator when all strains and species are taken into account. For now, our main working hypotheses are that Colony morbidity and mortality results do indicate cumulative stress. This means that individual colony managers can collect and use excellent data from their facilities for future planning. Next, increases in stereotypic behavior and potentially IBA can help indicate cumulative stress. We should be looking out for these during welfare assessment, but keep in mind the different ways that biomarkers might present in these behavioral profiles. Taken all together, it seems likely that there are alternative and opposing patterns in cumulative welfare indicators, and these should be considered during both animal welfare assessment and in future research. Thanks so much. Any questions?